Okay, so the next axiom is the axiom of union. That's a fairly mundane axiom. We don't get a lot from it, really, not immediately. It just ensures that for any two sets, their union exists and is a set, so that's kind of something we knew we wanted to have, and now we have it. The next axiom is the axiom of power set, and it turns out that that actually gets us quite a lot once we have it. So for one thing, of course, it says that for any given set, the set of all of its subsets is in fact a set and exists as a set. So that's what it says directly. From that we can get a good set theoretic definition of the Cartesian product of sets, which you'll recall is the collection of all ordered pairs with a left coordinate coming from x and a right coordinate coming from y. Now, if I am going to state that, express that in some way, I need to say what is the parent set from which I am selecting, and how do I know that the set of all pairs exists. I don't necessarily, but let's look closer at what the ordered pair xy is. Now, if you told me just x and just y, of course, I could argue that the set of, the ordered pair exists. We already talked about that with the pairing axiom. But what I need to have is a set that contains all things like this, not just, you give me any two and I can construct the, set that has them like this. So what set, or how can I ensure that there exists a set containing all elements like this? Well, if you look at the power set of the union, it seems like a pretty clear natural guess to look at the union because we have a thing like this, and then the power set, because the power set will have that as an element. All right, it'll have a whole lot of stuff, but eventually somewhere along the line you will find, in fact, the singleton of x, because after all, x is in the union, and therefore the singleton of x is a subset of the union, okay? That must be in the power set of the union. Also, you will find the set xy, because after all, that is a subset of the union too. Now, what we really want, though, is the set of these two things, and you do not find that anywhere here in the power set of the union. So, if you take power set one more time, take the power set of this power set of the union, now you will have a whole lot of stuff, but somewhere along the line you will encounter the set containing each one of these, namely the set of the singleton together with the pair. So in fact, this we are guaranteed to exist as a set because we are guaranteed that the union of any two sets is a set. The power set is, so is the power set taken again. So we know that this exists as a set and has all things like this inside of it. Now, we don't want all of those because, this set will also have things that are not just ordered pairs where the left coordinate comes from x and the right coordinate comes from y. We'll also have ordered pairs where, in this set here, more than the ones that we want, like namely we'll have ordered pairs where the left element comes out of y and the right element comes out of x, and we'll also have other things that we wouldn't even really regard as ordered pairs. So we don't want all of these things, but we do want to select from them. And namely, we want only those where the left coordinate is in x and the right coordinate is in y. Okay, I think it's pretty clear that we can get, products of products. That's not terribly hard to understand here. You also get relations built out of this, but I'm going to discuss that and other consequences in the next video.